Now that you know about electron configuration, we're going to insert orbital notation as well as a little bit of vocabulary. So the first vocabulary word you need to be familiar with is isoelectronic species. Now I'll break down this a little bit and hopefully help you remember, but iso means the same. Remember on an isotope, they had the same protons and different neutrons. In isoelectronic, they have the same electrons, or the same electron configuration. For example, argon has the electron configuration shown here, and chlorine has an electron configuration that's similar, but it ends in 3p5. However, if you make chloride, which has a -1 charge, that means it gained an electron. So now it also is isoelectronic with argon. Sulfur, similarly, has the same electron configuration but a 4 on the p. However, if it's -2, that means it's gained 2. So that would change it to 3p6 as well. Calcium actually has more electrons than any of these. It's 4s2 for its electron configuration. But if it's +2, that means it's lost 2 electrons, so it loses these 2 to again be the same as all of these others. Potassium is 4s1, and again, +1 means it's lost 1, so it is identical to these. So all of these are isoelectronic. They have the exact same electron configuration, but they do not have the same radius. So if you think about their orbitals around their nucleus, they're actually not equal, even though they have the same number of electrons in them. Argon, chlorine, sulfur, calcium, and potassium all have different protons. So the protons in the center are pulling the electrons in. So the one with more protons, that's calcium, is going to have the smallest radius because it's going to pull its electrons in tighter. And the one with the least protons, that's sulfur, is going to be the biggest because it can't pull its electrons in as much. So you need to be able to recognize isoelectronic species or figure out if things are or not isoelectronic. And then if you have a set of them, you should be able to figure out which one's the biggest. That's going to be the one with the least protons, and which one's the smallest, having the most protons. Alright, now let's talk about orbitals. Hopefully you saw orbitals in the POBL, and you should have seen these rules there as well. Each orbital can hold a maximum of 2 electrons, and those electrons are going to have opposite spins. So that's going to be an up spin and a down spin. This is ruled by the off-ball principle. If you have more than one orbital in a subshell, for example, P has 3 orbitals in its subshell. Remember in the pink room there were 3 bunk beds? Same idea. So in the P subshell there are 3 orbitals. In the D subshell there are 5 orbitals. And in the F subshell there are 7 orbitals. But if you have more than one orbital, like you do in these, you're going to put a single spin up electron to each orbital before you start adding spin down. Now, before we leave this rule, I want to clarify. This could also be reversed. You could add a single spin down before you start adding spin up electrons. So these words could be flip-flopped. The key is you put them in going the same way before you double up. Okay, and that is Hund's rule. All right, so let's look at that in action. Lithium has 3 electrons. And we know from earlier that lithium is 1s2, 2s1. So it has its 1s orbital with 2 electrons in it. Notice they have opposite spin. And its 2s orbital with 1 electron in it. And notice the up spin that it has. Okay, this could also be a down spin, but normally we do our up spins first. All right, what about fluorine? So we saw earlier that fluorine is 1s2. So there's the 1s with its 2 electrons, opposite spins, 2s2, so there's the 2s with its 2 electrons, opposite spin, and 2p5. Now we said just a second ago that p has 3 sublevels. So that's why you see 3 orbitals drawn here in the diagram for 2p. 3 orbitals, 5 electrons. So we would put 1 in each, 1, 2, 3, before we come back and double 4 and 5. Okay, so that is how we make orbital diagrams. That's what you see here. All right, for nitrogen, nitrogen has 7 electrons, so that's 1s, 2, so 2 electrons with opposite spin, 2s2, 2 electrons with opposite spin, 2p3. So we have 2p orbital, we have 3 orbitals there because 2p has 3 orbitals in that sublevel, and there's 3 electrons. So here they have 3 electrons, but there's something wrong. What are they doing wrong here? Why is the X on this? They are not following Hund's rule. Hund's rule, okay, is being broken here. Oh goodness, I'm butchering this. Sorry. Hund's rule. So let's look at how that should be done. For nitrogen, we should have 2 in the 1s, which we had correct before, 2 in the 2s, and then for these 3 in the 2p, we've got to go same spin, 1 in each before we ever double. Okay, so we place 1 unpaired electron in each orbital. They got to have the same spin, so they could all be down or all be up before you add them in the opposite direction. This creates a lower energy system. Okay, just think about it. You do not want to share a room with your brother if there's an extra room in the house. You're going to spread out. Okay, same thing with electrons. I don't know, maybe you like your brother. But electrons are all negative. They don't want to be in a space together if they can avoid it. So they're going to spread out if there's more rooms available, like in the p and the d and the f orbitals. All right, last little piece of vocabulary here is para and diamagnetic. Para and diamagnetic. So let's talk about what that means. Paramagnetic atoms are atoms that will be attracted to magnetic fields. Paramagnetic are attracted to magnetic fields. Now think about it. They pair with electrons. Okay? This is the part that's kind of confusing though. Why do they pair with electrons? Because they have, why do they pair with magnetic fields? Because they have unpaired electrons. Okay? So paramagnetic atoms are attracted to magnetic fields because they have unpaired electrons. So for carbon, this is its orbital notation. It has 1, 2 unpaired electrons, so it is paramagnetic. It will be attracted to a magnet. All right? The opposite is diamagnetic. These are repelled by magnetic fields. So I say they die in the magnet, repelled by magnetic fields, because they have no unpaired electrons. So neon gas, for example, is diamagnetic because neon gas has no unpaired electrons. Right, so make sure you review and are familiar with that vocabulary word. You should be able to apply it. If you draw an orbital notation, I could then ask you, okay, is this atom diamagnetic? All of them are paired. Or paramagnetic, where it has some unpaired electrons.